Hello everyone, thank you for watching my presentation today. My name is Joe Coker. I'm representing the physics department at Hendrix College, and today I'll be presenting on the design and implementation of 3D printable optomechanical components. The work I'm presenting was done in collaboration with Julie Gunderson, Dylan Mitchell, Ryan Bullis, John Stewart, and Bill Gunderson. One of the biggest obstacles facing college and university natural science departments is that the equipment used in analytical techniques is very expensive. There are many techniques, widely used in STEM fields, that need sensitive and precisely engineered equipment to be carried out accurately. Even a device that just consists of a series of lenses and mirrors bolted to a laboratory workbench can cost hundreds of dollars. And when a department needs several such devices to have enough to use in the classroom, the costs can get exorbitant very quickly. So it would be beneficial to have a cheaper alternative available. Now to that end, for the past few years, our research lab has been working to develop computerized 3D models of commercially available optomechanical components that can be fabricated using a 3D printer. These models are then shared with the scientific education community using open source platforms, which makes teaching analytical techniques accessible to departments with limited financial resources. One device our lab has reproduced using 3D printing is a Michelson interferometer. This is a device in which a beam of light from a laser is directed through a dichroic mirror. A dichroic mirror is a pane of semi-transparent glass that allows some light to pass through and reflects the rest. The divided light beam is then directed toward a pair of normal mirrors, which bounce it back to the dichroic mirror, which then recombines it and directs it to a viewing screen. Separating and recombining the light beam like this causes an interference pattern to be created in the light, and that shows up as a bullseye pattern on the viewing screen. This device is used in the physics classroom to let students directly see the wave nature of light. Our setup consists of 7 main parts: a laser mount, a holder for the dichroic mirror, a pair of kinematic mirror mounts whose angles can be adjusted so the beam remains in alignment, a viewing screen, and a pair of focusing lenses to modify the beam shape. This picture shows the mechanical components of 2 workbench Michelson interferometers. On the left is an interferometer made of commercially bought machined metal parts, and mirrored to it on the right is one made of parts 3D printed in our lab. Each of the 7 components requires a mounting base, a post holder, and a post in addition to the component itself. And as you can see from the price breakdown of the components, the cost of all these parts adds up quickly. Even without including the optical components, so the mirrors, lenses, and laser, putting together one Michelson interferometer from commercial parts costs about $400. However, printing the parts and assembling them in the lab, as we did, only costs about $30 for the plastic filament. That's a markdown of more than 90%, and it makes the study of this technique much more accessible to departments with limited funds. This picture shows, on the left, the interference pattern created by the commercial interferometer, and on the right, the one generated by the 3D printed device. And while the pattern generated by the commercial parts is certainly more precise than the 3D printed one, it's still safe to say that the 3D printed interferometer is more than sufficient to be used in an educational setting to demonstrate the wave nature of light. So, to sum up, we've shown that by utilizing 3D printing technology and open source platforms to share designs, university and college STEM departments can give hands-on experience with sophisticated instrumentation at a greatly reduced price. Not only does it save money, but printing and assembling their own parts also gets students much more involved in the experimental design process than they would be if they were just assembling parts out of a kit. And finally, while 3D printers are not exactly cheap, you can get a decent one for between $500 and $1,000. And that one-time investment will quickly pay for itself since it can be used for any number of experiments. There are a few drawbacks to using 3D printed parts instead of commercially bought ones. One is that the plastic parts are not nearly as sturdy as the machined metal ones. But one of the beauties of 3D printing is that if a part breaks, you can just print another one, so it's a pretty minor disadvantage. The main disadvantage of using 3D printing is that it takes a long time. Printing all the components for one interferometer took about 12 hours. But another benefit of 3D printing is that once the printer has started a job, it doesn't have to be supervised. So you can always start it, leave to work on something else, and come back when it's finished. As far as future research along this path, the principle of substituting machine parts with 3D printed ones is one that can be applied to all kinds of scientific instruments. I'm currently working on a device we call the Fluorino, which is a workbench fluorometer made of 3D printed parts that uses a microcontroller called an Arduino to measure the fluorescence of chemical substances. This presentation was based on a paper published by our lab in the Journal of Chemical Education in 2020. Thanks for listening.